In this video, I introduce diffusion probabilistic models in machine learning. Diffusion probabilistic models define a forward diffusion process that converts any complex data distribution into a simple tractable distribution, and then learn a finite-time reversal of this diffusion process that defines the generative model distribution as shown here. A labeled data distribution Q is gradually converted into a well-behaved distribution pi by applying Markov diffusion kernel T pi for pi y, as shown here. Where beta is a diffusion rate, in the forward trajectory, T steps of diffusion are required from Q x0 to pi y, as shown here. The generative distribution P will be trained to describe the reverse trajectory P, as shown here. For Gaussian and binomial diffusion, the reversal of diffusion process has the identical Markov kernel function as a forward process. Namely, for a small beta, if Q is a Gaussian or binomial, B is also Gaussian or binomial. So probability that the diffusion generative model assigns to the data distribution x0 is defined as here, which is intractable for practical problems. Diffusion models use the annealed importance sampling to compute the relative probability P of forward and reverse trajectories, averaged over forward trajectories, as shown here and explained in this figure, which can be evaluated rapidly by average over samples from the forward trajectory Q. If the forward and reverse distributions over trajectories are identical, only a single sample from Q is required to exactly evaluate the integral here. Diffusion models are trained by maximizing the log likelihood, as shown here, which has a lower band by Jason's inequality. For diffusion trajectories, the inequality equations above here is rewritten as here, where D, KL, and H are KL divergence and entropy respectively, which can be analytically computed. Training diffusion models is to maximize the lower band on the log likelihood. For more details, please check with these references. Thank you. Bye.